Welcome, everybody. Thank you for joining us this afternoon. Looking forward to this discussion on our recent research we did on e-fuels, whereas we worked with ERM. We've got Randy Courtwright, research advisor with National Renewable Energy Labs, and John Eichberger with the Transportation Energy Institute to go over a summary and a look at the e-fuels report. And I just wanted to kick it off by saying that this report, I think, is the epitome of TEI. It's jumping into something that what could be and dissecting it as to, how do you move it forward? When is it going to move forward? What are the hurdles? And looking at all of those pieces. And it's really what I think TEI is very, very good at. Putting all biases aside, looking at a new technology that's quite frankly amazing, we can say, what do we need to do to make this happen? And I think that's the end result of this report, in my humble opinion. But anyway, I'm looking forward to this. This is going to be recorded and available for later viewing for those that couldn't join us. So I think at that point, I'm going to stop speaking, because the more I speak, the more likely John's going to get nervous. So I'll pass it over to John. And if you want to kick us off, that would be great. And let me know what I missed.
Thanks, Jeff. So this is the study he's referring to. We published it last fall. It's funny, we're working on a different study right now, looking at about 9 of our reports over a 5-year period. And you can see a trajectory, as Jeff mentioned. We do a lot of research which will indicate a potential opportunity. This is one of them, came up in a couple of studies where e-fuels are a promising technology to decarbonize combustion vehicles, and especially the hard to abate markets. And that led us to commission this report to dive deeper into it, to really evaluate the viability of it. So what I'm going to do is I'm going to walk through some of the highlights of the study. I'm going to do it kind of quickly because I want to give Randy enough time to chat about what he's learned from his experience working in the sector, and then leave plenty of time to chat afterwards. So first of all, about Transportation Energy Institute, if you're not familiar with us, hopefully everybody is. We're a non-advocacy, non-profit research group. Our board of advisors is represented here. There are some that aren't up here that are just subject matter experts, maybe retired or individuals. But you see the broad diversity, and our board decides what we study. They peer review everything we publish. And if you think about how do you come up with an objective organization, the strategy is you get enough people on the board who have different opinions and different objectives, and you give them equal say in the peer review process. If there's anything in any of our reports that's biased, I guarantee you somebody's going to find it. So I'm very confident in saying that the research we put out there is fact-based. It is as objective as you're going to find in the market. And that's, I think, the hallmark of what the Institute's all about. So let's take a look at the study itself. Why did we study it? You see on the right-hand side, we need to find a way to reduce emissions from existing and new combustion engine vehicles. When we commissioned this report at the end of 2023, everybody's talking about electrification as the only strategy, and we're very cognizant of the fact that in the world, there's 1.5 billion vehicles currently in operation. To replace all those with any new technology is going to take decades. And if we care about emissions reduction, we need to be thinking about it now in terms of how we reduce emissions from the existing fleet and the millions of combustion vehicles being sold every year. The key questions are there in the middle. Okay, what are they? How are they produced? How can they be used? What's their impact on the environment? How much can we produce? What's the cost, and what policies have to do to support it? So Jeff mentioned ERM is the company that did this research for us. They've got extensive experience globally, and we really wanted a global perspective on this because so much of the momentum on e-fuels is global. And so we'll take a look at the regionality of it in a little bit too. First of all, what are e-fuels and how can they be used? My guess is most people on the call know what they are. But if not, they're renewable fuels. So they're a liquid fuel that is produced from water, renewable electricity, and carbon dioxide. Carbon dioxide is captured either direct air capture or from industrial processes. One of the things that has always appealed to me about it is the fact that once we produce the fuel, depending on what the end product objective is, a lot of it is drop-in. It is a gasoline alternative, a diesel alternative, a jet fuel alternative. Some of it is blend restricted. So there's e-ethanol, for example, e-methanol. But they're fuels that are not going to require infrastructure changes. And years ago, I was invited to sit on a panel with NREL at a conference to talk about e-fuels. I didn't know much about them, but my big point on that one was, if they are truly dropping and we can scale them, we could reduce emissions almost 100% without any infrastructure changes, without changing any consumer behavior. That's one of the reasons I'm so interested in it. Now, one of the three technical reasons we were interested in doing this is the GHG emissions reduction could be as high as 99%, depending on the pathway and the energy used to produce it. Again, compatible with infrastructure and vehicles, almost drop in for most of the products, and they're produced from abundant resources. We're not running out of CO2. We're not really running out of water. We're not really running out of the ability to produce renewable electricity. When we look at the opportunities and the resource availability domestically in the United States, we're not even scratching the bottom of the barrel in terms of the resources that are available that would be used to produce the volume of e-fuels we might be able to produce in the United States. So great opportunities here, but with every opportunity, there's challenges. Years ago, when I was a lobbyist, I was told, John, you're the most pessimistic person in the world. I said, no, I just recognize that everything we're trying to do is going to have hurdles. We need to identify those hurdles, because only then can we develop strategies to overcome them. And that's really what this paper is about. It's helping us identify how we get from where we are today to where we might need to be or want to be with this product in the future. We are still at the very early stages of production technology. Demonstration projects really in operation the last couple of years. You can see the 5 primary production technologies. The second columns are technical readiness level, which is explained on the right-hand side. It goes from 1 to 9. The most advanced are at a level of 7, which is a system prototype demonstration operational environment. But you go up further, you're still in technologically validated, technology demonstrated. So we haven't gotten into really marketability yet, but the investments, the research and development is there to get us there. But we are at the early stages. So a lot of what we know about it is limited. A lot of what we know about the potential is speculative because we haven't gotten to mass scaled production levels. But we have enough knowledge to give us some insights of where that might go. And that's what we're going to look at in a little bit. Environmental impact, again, could be up to 99%. Now, that is all based upon your assumptions. And so today we're going to look at 2 primary cases that were modeled in the study, the base case and the low greenhouse gas emissions case. I've circled the critical elements. So we're going to use renewable electricity to produce the hydrogen. In the base case, we're going to take CO2 from cement plants, where a lot of CO2 is produced and emitted. We're going to capture it at the cement plants. In the low GHG, we're going to directly capture it from the environment. Much more expensive and complicated, but theoretically, it's a brilliant idea if we can figure out how to make it cost effective. Electricity for fuel processing in the base case is grid electricity, which we know can have a high carbon intensity. In the low G, it's all renewable, and it's all additional renewable. And then heat for the fuel processing, we're going to use natural gas in the base case, which is methane based, and then we're going to use renewable energy in the low GHG case. So clearly, low GHG requires a lot more investment, a lot more technological advancement than the base case. But even so, when we look at the base case, only one of the product pathways has a higher carbon intensity than the petroleum product, fossil product it is replacing, and that's the ethanol to jet process. Every other process, the Fischer-Tropsch, the methanol to gasoline, methanol to jet, e-ethanol, e-methanol, e-methane, are all lower carbon intensity than the fossil product they're competing with. And this is representative of the early e-fuel plants. This is not even taking consideration advancements in process technology, facility design, and again, it's the base case. It's not using the renewable components required in the low GHG case. If we go to the low GHG case, however, pretty much we're at 99% loss of reduction in GHG emissions. Direct air capture, renewable heat, renewable electricity. So again, much harder to achieve this, much more complicated, much more investment technology and resource intense. But the end product is outstanding. And if you were to take a product like this and put it into a modern combustion engine, you're not going to have very much emissions on a life cycle basis. We did a life cycle assessment study in 2021, I believe we published it, and basically said, 75% of emissions come from the fuel the combustion engine uses. If you remove the carbon and the GHG emissions from the fuel, you reduce 75% of emissions. Now you throw in maybe a hybrid technology or advanced higher fuel efficiency vehicle, you're getting even greater. So huge environmental potential. Now, again, I use that term as potential. A lot of people can quibble with these numbers, but when you're looking at reductions of this magnitude, anything in that neighborhood is going to be a significant improvement over the current product we have in the market. Of course, the best idea and the best concept, it means nothing if it can't reach the consumer. I think since day one, we launched the institute, I said, whatever your solution is, no matter how brilliant it is, how fantastic it is, if the customer can't access it or can't afford it, you're wasting your time. So how much can we produce and how much can we rely upon from the e-fuels market in the future? Looking at existing production plans and scales that ERM has access to, they project that in the central scenario, which noted in the is ambitious but potentially realistic based upon what they're seeing in historic trends, we could produce 27.5 billion gallons of e-fuels a year by 2040. Now, how significant is that? We consume a ton of fuel, so it's still a small percentage. But when we ran that volume through the TEI's carbon avoidance tracker, which uses the GREET model to calculate emissions reductions, we're reducing carbon emissions by 244 million metric tons a year. So even though it may not be a full replacement, again, there's no silver bullet. There's nothing that can replace every single vehicle in the world. But it is making advancements in emissions reduction at a pretty significant clip every year. Where is production being centered? 48 commercial plants are planned in Europe, 5 are in the United States. You can see the breakdown by technology, by location. Clearly, the bigger it is, the more volume you're looking at. But we're seeing a diversification. You've got plants planned in Australia, South Africa, South America, Asia. This is not a domestic initiative. This is a global initiative. And that's another thing that appeals to me is transportation's not a domestic concept. Reducing emissions does not recognize borders. Being able to contribute a fungible product that can be distributed throughout the world is something that really makes e-fuels a higher potential product than some others. And so really understanding that trade basis, the distributability of the product, and the fungibility in the system is really important. In the US, the projection is maybe close to 5 billion gallons by 2040. And the question is raised, do we have enough renewable electricity and carbon dioxide? And the first chart there, I did notice today reviewing this, we have a comma out of place in the second column there. But renewable electricity today is 890,000 gigawatt hours per year. Potential through 2040 is 460 million gigawatt hours. The renewable electricity required for e-fuels is a small fraction of both of those numbers. You look over carbon dioxide emissions, again, a very small fraction. These bars aren't to scale because you won't be able to see some of them, but a very small fraction of what we're going to need to produce that 4.7 billion gallons. Now, that doesn't mean the renewable electricity is connected where it needs to be connected. Doesn't mean it's being produced where it needs to be produced. Doesn't mean the carbon dioxide is being captured where it needs to be captured. So there's hurdles we need to overcome, logistics. But the capability, the potential is there. And that there is encouraging to me that it's something we need to continue to watch and pursue and see how it plays out. Ultimately, what's it going to cost? I said if customers can't access it or can't afford it, it will fail. If e-fuels don't come down in cost, they're going to struggle. Everything comes down to economics. There are people say reduce carbon at all costs. That's just illogical. If something costs too much, the market will reject it and it will fail. We need to find solutions that are cost competitive. Right now, e-fuels are 2.5 to 4 times more expensive than the fossil fuels they replace. And that's based upon ERM's analysis. You can see the assumptions that they included here on CO2, hydrogen, electricity, and heat. This does not include all the renewable stuff. This is more of the base case. If you look at the low GHG scenario, those numbers are going to go up. So we're looking at a pretty high cost product, but that doesn't mean it's going to stay that way. So what ERM did is they took a look at first of a kind facilities, which are those, the FOAK, being produced or designed now. And then they extrapolated technological advancements through 2040 to see what might be the net levelized cost reduction over the next 25 years or 15 years. And what you see is every single pathway goes down in cost. And that's an encouraging thing. Now, the big question is, do they go down enough? When we look at current plant configuration and we look at domestic policies that existed in 2024, some of these have changed. We know that. But it was the 45V, 45Q, 45Z tax credits. Okay. If we were to stack those on top of one another, even under first of a kind plant technology, we can get the majority, not ethanol to jet, but the majority of pathways can get close to or below the willingness to pay threshold. So this is indicating that we do need policies to help drive those prices down. If the policy stack was what existed last year and the year before, there is a potential that these pathways could be cost competitive with existing plant technology. If we move forward to future plants, the nth of a kind facility, the perspective maybe 2040, almost every single pathway, with the exception of ethanol to jet, is lower than the willingness to pay threshold. This is an encouraging dynamic. It requires policy support, which is eroding right now, but there is still potential. It's only eroding in the United States. And we have to keep that in mind. There's a lot happening in Washington, a lot of things that were being built in previous administrations to support alternative fuels and carbon reduction are being dismantled and changed. That's only domestically. That's not happening in Canada. That's not happening in Europe. That's not happening in Asia. And so we need to keep in mind that in a global market, thinking that changes in prioritization of the White House are going to affect the global trajectory is misleading. Yes, the U.S. has a significant influence on the direction of technology and investment and world politics, but it is one of many that have an influence. This is one example of if the policies are structured appropriately, e-fuels could be cost competitive in the next 15 years. So I'm going to wrap up here and give it over to Randy. My takeaways are, look, combustion vehicles are not going anywhere. They're going to be here for a very long time. We need low carbon fuels if our goal is to reduce carbon emissions from transportation. We cannot replace our way out of our current emissions profile by bringing new vehicles to market. Most e-fuels are drop-in fuels, and they have a potential to reduce carbon emissions by up to 99%. Production over the next 15 years could hit 27.5 million gallons, and they could be price competitive if the technology and the policies align. It requires a lot. It requires a lot of things to line up. The plan is to align properly. But if you think about the forecast on electric vehicles being half of all vehicles sold in the United States in 2030, those forecasts required a lot of plans to line up too. So, looking at the potential does not mean that's going to happen that way, but it also means that there's a pathway to get there. It's just a matter of how dedicated we are to get there. Strongest demand for e-fuels come from the aviation sector because it's a little more price insensitive. They're going to be more expensive, and we need the policy to make it up. The key here is, again, before I give it to Randy, this is a product that could contribute to the decarbonization pathway of transportation. It is going to be kind of expensive, but there are ways to reduce those costs. If governments were to get behind this, the opportunities are really strong. And I think there's a huge opportunity here, but it all comes down to that scalability and the reduction in cost and the combination of policies. If it's not cost effective, it probably isn't going to take a big chunk of the market. But if it does become cost effective, I think there's tremendous upside opportunity here. So with that, I'm going to turn it over to Randy to walk us through his perspective on e-fuels.
Thanks, John, and great presentation. Just to give you a little bit of a sense of my background, before joining NREL, I was actually working at a company I founded called Virent, where I worked for 20 years in conversion of biomass to generate drop-in fuels such as gasoline, jet fuel, and worked with a number of people within that sector. So I have an experience in the idea of alternative fuels for transportation as well as chemicals. And before the startup company, I actually worked in industry for a company called UOP, where I worked with petroleum-based processes to generate jet fuel, gasoline, and those types of things. So to give you a little bit of perspective of where I come from with these things, as well as explain to what we're trying to do here at NREL in the areas of e-fuels. So kind of following up, you can go to the next slide, John. I guess you guys are driving, right? Yeah. Okay. So I think what John has kind of shown is that there are technologies that are out there. People are able to do analysis on it. From a cost perspective, e-fuels aren't quite ready for prime time, primarily, because it is a newer technology. And so I like using this report from McKinsey, where they start looking at what do the out years look like. And I think there is this idea that we may not be ready today, but if you put out into the next 10, 20, and 25 years from now, there is this projection that e-fuel costs would be coming down. They would become the lowest cost alternative. So is one of the things you'll be hearing me talk about, that there are other ways of getting to these drop-in fuels, be it utilizing fats, oil, and greases to make HEFA, doing gasification of particularly biomass, followed by Fischer-Tropsch. The alcohol, the jet, John's kind of covered a little bit of that. And then the power to liquids is really getting into the e-fuels. And what we're talking here is I've done a lot of work within jet fuel. Taking it one step further, next slide, please. And as far as the timing goes, and this is now a place where there will be the idea of market pull. As John mentioned, the United States, over the last year, we have pulled back from some of our initiatives that we had a year ago, but we are still seeing worldwide people moving forward on this. And one of the main market drivers, I think, that will be pulling some of these e-fuels into the marketplace will be out of the EU, with this EU Commission kind of mandate where they're looking to start blending sustainable aviation fuel into jet fuel, with the idea that some of it will be from waste materials, recycled carbon primarily. There is idea of being able to use HEFA and that sort of stuff within it. But most importantly here for this conversation is they have also mandated that a certain fraction of this will come from pathways which we would call e-fuels or e-SAF. And what I like looking at here is they're looking at, no, there's not going to be a big market in the next 5 years. We will be giving people a sense like a demand in the range of 170 million gallons of these e-fuels by the 2030 timeframe, growing to a little over 700 million gallons by 2035. And then you can see by 2050, there'll be 7 times that. So then we'd be looking at significant amounts of e-fuels that would be required for within the EU. And this gives industry a chance to start scaling these technologies. Yes, it's going to be expensive at the beginning, but the blend rates are going to be relatively low. Therefore, that cost doesn't have to be passed on to consumers. It won't be a big burden at this point in time. We can go to the next slide, please. So John kind of covered a lot of the different pathways. From my background and what I've worked with in the chemical engineering field, I'm less worried about the back-end technologies. The routes that I'm showing here at the top of going through methanol, where once you can generate methanol, you can make gasoline and e-gasoline. You can start making distillate, which can go into but either jet fuel or diesel. And then there's the Fischer-Tropsch route, which has been around for a number of years. These are technologies that today you can go out and license from a technology provider. You can go to the Shells, you can go to the UOPs, you can go to the Axums, the Halder Topsoes, and that sort of stuff, and license this technology, and they'll guarantee it. There are other alternative routes that people are working on that primarily what they're going to do is reduce the number of steps. But when you start looking at these different routes, they kind of need the same number of pots and pans, meaning reactors and separation systems, to get a fuel that's going to meet specifications that you can drop in to either use it as gasoline or use it as jet fuel or use it as diesel. So they kind of have the same number of steps. There is some process intensification that can take place to help bring that cost down. But my point here is these technologies are already there. So the issue that I see from a cost point of view is, where does the feedstock come from? And John has kind of mentioned is taking water to make hydrogen through electrolysis. And then what is the CO2 source going to be? So we can go to the next slide, please. So from my background from doing startups, I always do back of the envelope calculations to say, is this viable and where do I need to get to? So this is just a quick spreadsheet I put together. The assumptions here is I got a certain cost of feedstock, be it hydrogen, as well as CO2 going into the system. I just set a price, lowest cost alternative. John's kind of shown is could be within this $5 per gallon range. And then from my experience, I'm working with EPMs, with different types of construction firms and that sort of stuff. You know, we're looking at a capital cost on these back-end technologies in the range of $10 per gallon. And so what all these numbers are in here are just payback years. And my experience for people that are doing projects is they need a certain number of payback years. A simple calculation for them to even consider a project. So on this part here, all the stuff that's in blue here is you wouldn't do the project because the cost of your raw materials is much higher than the cost of your product. So that doesn't work. Things that are in white, yeah, it's kind of questionable where you're going to do it. The stuff that I'm showing you here in yellow is kind of the places where people be interested, where you're looking at a payback of around 5 years or so. And what this kind of shows is that in order for us to get there, we need to get our hydrogen costs down to less than $2 a kilogram. And we need to start seeing the cost of the carbon dioxide in the range of $100 to $150 a ton. Now, today, if you go look at electrolytic hydrogen, it's costing about $8 a kilogram. We have pathways to get to 4, but I'll show you in the next plot what we need to do in order to get that electrolytic hydrogen down in the range where this would make sense. And then we get into the CO2 source. And I'll show in a second, point sources, yes, we can get carbon dioxide at $100 a ton. If we start looking at direct air capture or direct ocean capture, we're looking at something that's going to be north to $600 a ton. So there's a lot of work that needs to be done on that. And there's the idea of looking at what should be the source of CO2 going forward. You can go to the next slide, please. So this is work that we do here at NREL. We have been working with DOE to understand how can we bring the cost of electrolytic hydrogen down, kind of focusing on these bar plot charts here. You can see the major cost for electrolytic hydrogen is going to be the electricity cost. And we're showing here going from 6 cents a kilowatt hour down to 1 penny a kilowatt hour. We maintain our capital costs kind of the same, but that's going to be one of the big drivers is getting that cost of electricity down so that this will be able to work. We do need to bring the capital costs down for the electrolyzers. We do need to improve the reliability of the electrolyzers. When I talk to people that are trying to put projects together on the electrolyzers, their main issue right now is liability. Who is going to guarantee these electrolyzers? And so it's a case that there are a number of smaller companies that have electrolyzers. While they may be a little bit lower cost, these people that are doing projects look at larger companies because of their balance sheets and they can cover some of the liabilities on this. We can go to the next slide, please. Coming back to the idea of electricity, we do a lot of work here at NREL, understanding the cost of electricity, both from being generated at the point of source. So what's shown here, this is in a particular market that we have here that we look at. We actually have models that allow us to go and look at a lot of different markets, but you can see here, this is Indiana, Michigan, Minnesota, Arkansas, Louisiana, and Texas. And what's showing here is that for most of the time of year, the cost of actually producing electricity can get us kind of into the range of what we need to bring the cost of electricity down. The issue is those peak periods where the cost gets to be very high, and then you have to have variability in operation of these electrolyzers. But there's also another thing when we start looking at electricity prices, you can go to the next slide, is that not only do we have to worry about the time of use, the hourly rate, but the utilities are going to put on what they call a demand charge. And this demand charge usually covers covering the capital recovery that they're having as well as their profits. So that's the other part that kind of comes into it. And we're trying to learn is the idea of what these power offtake agreements are going to look like potentially in the future. Now, many of you have seen in the news that there's a lot of worry right now because of all the data centers going in. Where's the electricity going to be coming from? There's the idea that now as we're doing more electrification of cars, where's the electricity come for charging the cars? We do need to increase the supply. We do need to increase it on the renewable side. So that's with both solar and wind, which, fortunately turn out to be low-cost sources of electricity. They do have the issue that they're only available when the sun shines and the wind blows, but there's the idea of getting those things on the grid to have more supply. The other thing that we're seeing and we've been following is one of the things with this current administration is they are pushing nuclear. And there is a case that nuclear is not the nuclear that we knew 30 years ago. There's been a lot of advancements been taking place, and it's a way of how can we now have nuclear power that we consider safe, and we have been able to take care of whatever the waste disposals could be in that area. So that's going to be something in the future that I think is going to come about that's going to allow us to drive the electricity prices down. We can go to the next slide, please. So now coming to the CO2 parts of it, there's the case that, John kind of showed, there's the point sources of CO2. This can be from power plant plants. It can be from cement plants. I'm going to talk a second here. It can also be biogenic CO2 from biomass. And all these have kind of different carbon footprints that we can follow. We're doing a lot of work with startup companies that are doing direct air capture. So this is the idea of being able to capture the CO2 out of the atmosphere by blowing across either an absorbent or some sort of liquid solvent. And then there's been interest in the idea of direct ocean capture, where there is already an equilibrium of the CO2 in the atmosphere with the amount of CO2 in the ocean. The ocean is generally a little bit more alkaline, and it can capture the CO2, and you can see higher concentrations of the CO2 from that. So people are looking at potentially getting the CO2 from actually ocean water. We can go to the next slide, please. So it is a case from the point sources, and as I kind of mentioned, that now getting into that range of $100 a ton, there's a number of point sources where we can get there and be below. Cement is, the example that was shown in the report, kind of gets you into a reasonable place. Power generation, hydrogen production, this is doing steam methane reforming, which kind of gets into what you use for ammonia. So those are places where you can get low cost CO2. One of the places here will be the ethanol production, where the ethanol production is actually a fermentation of biomass. Of all these routes here, that ethanol production would potentially give you some of the lower carbon intensities at this time. And people are looking at doing e-fuels as an add-on to the current ethanol plants going into the future. But now coming back to the direct air capture and direct ocean capture, we can go back to the next slide, please. We got to fight thermodynamics here. So I like using this plot here. This is really kind of showing the idea of the CO2 and the feedstock. That's what's on the x-axis. So that's the initial mole fraction. So it's going at 1, that's 100% CO2. But then it goes all the way to the range of now when we're looking at the 400 part per million, or the amount that you're going to find in the ocean. And it's a case here that what we're showing here for this, the amount of work it's going to take to do that separation, get it concentrated, is going to be relatively high the more dilute the system is going to be. Where you can see if it's 100%, it's 0. And what I'm showing here is theoretical. If we can get in that range, it's going to be reasonable. But right now, and this is why the cost for direct CO2 from direct air capture is so high. Right now, that actual energy and the efficiency of these type of systems is at least an order of magnitude higher. So one, that's the bad news. That's why it's so costly. But the good news is there's room that we can bring that cost down. So with that, I think that was my last slide. Oh, sorry, I got 2 more slides. I just remembered this part of it. So I want to come back to the biogenic CO2. I already mentioned the CO2 from corn ethanol. When we look in the United States, that amount of CO2, if we convert that now into e-fuels, using this conversion of 100 gallons per ton of CO2, you can see that there's potential from a corn ethanol plant of close to 4 billion gallons of e-fuels that can be generated. Now, if we start looking at other types of biomass that we can use, one is black liquor combustion, which is already being done at paper mills and pulp mills. If we actually capture that CO2, that adds another 7 billion. If we take a look at woody biomass and do combustion, I'm going to talk about that in the next slide. You can see it. We can actually increase it even more to 14 billion gallons. So, and then there's the idea of being able to use landfill and anaerobic digestion that can add up to 300 million gallons. So one of the concepts that we're looking at here now is taking this biomass and then reducing the cost of separation. So we can go to the next slide. And a technology that's already available and you can license is an oxy-combustion of biomass. And the idea here is having oxygen, air, oxygen removed from air, just oxygen to burn the biomass. You generate CO2 and water from that combustion, and then you just have to condense the water out, and then you have the CO2 available. Now, this BECCS part of it is you're generating energy and you're doing carbon capture. So it's kind of twofold. It's actually one of the things that we started taking a look at. If you combine this with an electrolyzer, it turns out that the electrolyzer to make the hydrogen that you need to convert the CO2 into e-fuels, the byproduct oxygen would be more than enough to be able to do this oxy combustion. So it's one of the things we're looking at is from an integration point of view, can we start utilizing biomass as the source of CO2? It isn't as low of a carbon intensity as what you get from direct air capture, but it would be much lower cost, and it would still easily fit what John was showing as far as having a lower carbon footprint than what you would see in from the combustion of fossil fuels. So with that slide, I think I am done. So thank you.
Randy, that was spectacular. John, amazing. Do we have we can open it up to questions right now if you want to throw them in the chat, or feel free to unmute yourself and speak up. And let's see, no questions in the chat right now. I will just start it off. I mean, Randy, you talked a lot about the cost of electrolyzers, and 2 years ago it was kind of almost synonymous with the battery discussion on electric vehicles. The cost of electrolyzers was just simply too high, and the reason for that I was given was because they weren't making enough. There wasn't enough demand for them.
Yeah.
And it seemed like at the time a very big driving factor for those that were poo-pooing e-fuels. In the last couple of years, could you put like a percent on how far electrolyzers have come down in costs? So
and it kind of gets into there's 3 different flavors of electrolyzers. There's the alkaline, there's the PEM, and then there's the solid oxide. It turns out that the alkali has been around. They were developed in Norway before World War II. And they were kind of a specialty one-off type of a system. They use relatively low-cost electrocatalysts, use nickel and that sort of stuff, compared to maybe the PEM and so forth. And coming to your point is that there wasn't a huge demand. They essentially made these things more as a one-off specialty type of a piece of equipment. Now with this ramp up, and particularly where the United States was a year ago, these companies that are building electrolyzers says, okay, we see there could be a demand. Electrolyzers, they're not a scale up issue, they're a number up issue. So you start looking at the automotive type of a model is you've got to bring the cost down of the different components that go into the electrolyzer. You follow kind of the automotive type of thing is like, okay, we're going to say, we're going to make 1 million of these things. We're going to need 1 million of these pieces or type of stuff. And your supplier says, okay, we can build the factories that now can bring the cost of those different components down. That's how you're going to see the cost of the electrolyzers go down in the future. It's going to be, it's just basically, they just need to see from the market, yes, we need a lot of electrolyzers. We're going to build the supply chain and now bring the cost down.
So with that in mind, have you seen upticks in production of electrolyzers?
Yeah, I mean, and again, there was all sorts of announcements of people building gigafactories here in the United States. I have to admit they have slowed down because of what's happened with the change in policy, but we're still seeing it in Europe that they are building the factories there and they are starting to build the supply chains there. And then I think the other place, and we might need this, but we're seeing China's going great guns in this area. Just like everything else, they are saying we're going to get into the electrolyzer business because they do see the future of it, and they're going to be able to bring that. They're going to be able to make many of them, and just like what they did with solar panels, just like what they're doing with batteries and everything else, they're going to bring that cost down.
Got it. Thank you. Oh, we do have one question. Should e-fuels focus on hydrocarbon fuels? I'm assuming that's what HC is, versus e-ethanol or e-methane, since both are viable biofuels. Okay, I read that wrong.
Yeah.
No, I think so. I think I'm reading it too. I mean, replacing hydrocarbon fuels with an e-fuel is going to give you the greatest bang for the buck on emissions. Biofuels already have a lower carbon intensity. Using the CO2 from ethanol plants, because the carbon capture strategy for ethanol production is strong. Capture that CO2, what are we going to do with it? Convert it to e-fuels to displace hydrocarbon fuels. I think that's got the biggest impact and biggest benefit associated with it. So that's my perspective.
Yeah, and I agree too. I mean, existing drivetrains are already optimized for utilizing this mixture of hydrocarbons. So anything you can get close to that will be very marketable at this time.
No other questions right now. I will just add a little update on the carbon capture pipeline in Iowa. That's been quite the debate. Is still being debated, but I think our governor pushed it forward. There was a question on eminent domain, and there was a lot of political upheaval over that. But there were a significant number of ethanol facilities that were primed to be along that pipeline to make it easier for capture, and whether that was capture and use or capture in deep well depositing, I do not know what their intent was with the end use, but obviously we got significant wind renewable electricity. I think about 50% of Iowa's renewable electricity is from wind. So we got a couple of the feedstocks here where this would really make sense. That was just my unsolicited comment. Any other questions right now?
And I'd point out your comment on wind in Iowa. In the report, there's a map of where the renewable electricity generation capacity resides in the United States. It's extensive. Now, the question is, can you take that generation and deliver it where it needs to be? But there's a provision in the consideration of e-fuels that the renewable electricity has to be additional, not just diverted, to really qualify for the benefits. But there's a ton of additional renewable electricity capacity. It's just a matter of how we connect it, how we deliver it, where it gets delivered, how it's used. But I think, we have an opportunity to really rely on renewable power if we take advantage of the resources we have available and have storage capacity to hold on to the intermittent power. If we can't store it, then we're wasting so much potential. But as battery technology improves, storage capacity will improve, and our options become much more plentiful.
Yeah, I agree. We really need to double down on renewable electricity. I think we got so much capacity for demand there. We've got so much demand. The other way that I've been thinking about it too is that if you are using the renewable electricity to create something like an e-fuels, you are in fact creating a storage. So the production of the
Yes.
renewable electricity might be intermittent, but you are still storing that energy in a liquid fuel tank.
Yeah.
So, maybe when we talk about logistics, it's about what are we willing to do? In this particular case, do we need that constant energy, which of course, to Randy's point, creates demand charges and makes things very uneconomical, or do we just flow with it and we use it as, we set a minimum, threshold for what we need for production and align with that. And then, right, something's better than nothing at this point. This whole is designed to be an incremental improvements over time anyway on feedstock. So it seems like there's ways where we could continue doing, more renewable electricity.
Yeah, so there is a part, and I think, you kind of showed the projects that are being planned and showing the United States. A majority of those are really in Texas, in the Panhandle, where they got huge wind resources. And it is a case that people are taking a look, and we're actually working with ARPA-E with the idea, coming back to the idea of having dynamic reactors so that they can do production when the electricity is available, but then they can be in standby mode and then be able to be ready to start doing production again when the electricity is available. And we're looking at some of those economics, and it's going to require some, reactor engineering and that sort of stuff, but we're getting some good ideas in that area as well. So the people are really looking at how they're going to tackle these issues. The other route that we've been working here at NREL is to kind of understand these demand charges and understand what these offtake agreements would be, power purchase agreements would be from utilities today, but also what they potentially could be in the future. And there is this part about as we get more supply and that supply becomes greener and greener, and I keep putting nuclear back in there, but we also have hydro, geothermal's another thing that we're looking at as well. As more and more of these resources come into play and they start building the supply, costs are going to come down, and people are going to be looking at, where do I put my electrons? And this will be another potential business case where we could have lower cost e-fuels as that energy storage media of those electrons.
Randy, where we put our electrons was a topic raised in our study. We did a comparison of the use of e-fuels versus other utilizations of these energy sources. And one of the references in there was that taking renewable electricity, putting it in an electric vehicle is a much more efficient use of the power.
Yes.
But my perspective on that is, but not every sector can be electrified for transportation.
Yep.
And so you need to have options for them as well. And if we can use the renewable electricity, to Jeff's point, to store that energy in liquid fuel form that can be used in those non-electrified capable sectors, I think that makes a lot of sense.
Yep. And again, people are somewhat resistant to change. That's why I showed, like, saying today e-fuels is ready. Well, some of the technology is ready, but I think if we start looking at the 10 to 20 years out, I do think they're going to have quite a bit of penetration into the marketplace. for a number of reasons.
That's really exciting. I keep telling people, 20 years ago, nobody was talking about electric vehicles being, the great new thing. They were kind of derided as we tried that, it didn't work.
Yeah.
And 20 years from now, what will we be talking about that we're not even considering today?
Exactly.
And maybe e-fuels is going to be the shiny new object in 15 years. And there'll be something on the tail of that's going to be shiny and new that's going to get everybody's attention too. It's just, human attention span is a little bit like a raccoon. If it's shiny, they want it. And the shiny and new always gets the attention. So that's one of the reasons, Jeff and I, we're very excited about what we do is we focus on what else. Let's look beyond the shiny new headline and see what else is percolating below the surface that might be the next great new thing.
Yep. And it's kind of the part, I've been in this renewable business now for 30-some years. And it's kind of like I've yet to predict a disruptive technology. and that's the great thing about disruptive technologies, but you got to keep working on this stuff in order for it to get there. I mean, it's the idea that people worked on solar and wind for years and years and years, and no one, if you go back 20 years ago, no one believed solar could get down to the cost they can get to, and the same with wind.
Yep.
And there you are. So
I believe always setting your objectives and your goals as ambitious as possible, because somewhere along the pathway, you'll find something that works and is better than what we started with.
Exactly.
So,
yep.
I'm done lecturing, Jeff.
Okay. Awesome. Well, I'll tell you what, that is one of the reasons too why we appreciate our relationship with the national labs too. A lot of the national labs, they really get out there and look in the minutia of different technologies and looking at the technology readiness and assessing on that on a global scale as well. And so because of TEI's relationship with the majority of the labs, at least in the transportation realm, it really benefits us, to coordinate and to work. So we really appreciate your time today, Randy.
Great.
Hopefully we get a chance to talk a lot more about this.
If you guys want to read the report, go to transportationenergy.org/research. It's chronological. It's down there, November 2024. There is the report, there's executive summary, there's other resources to take a look at. And if you have any questions about it, feel free to call any of us at any time.